Welcome to the 2022 edition of Adventures in Physics. Last year, we had a very great time with you. And if you had the privilege to participate, you must have picked up some nuggets that have possibly remained with you till date. Last year featured Duke Van Kantran, an author of mathematics from Texas University, and Professor Michel van Biezen from Loyola Marymount University. This year's edition is no different. Joining us again tonight is Professor Michel van Biezen of Loyola Marymount University of Los Angeles, whom I'll briefly introduce to you shortly, and Sara, the Students Ambassador Coordinator for the American Physical Society, who will share with us relevant information as far as Students Ambassador membership is concerned. I entreat you all to get comfortable in your seats and expect to learn something from this year's edition of Adventures in Physics. My name is Kevin Yeboah, the Student Ambassador of the American Physical Society, and I'm your host. Thank you. The American Physical Society is a non-profit membership organization working to advance and diffuse the knowledge of physics through its outstanding research journals, scientific meetings, and education, outreach, advocacy, and international activities. Joining the American Physical Society is the perfect way to stay connected with the most recent developments in the world of physics. Tonight, APS Ambassador Coordinator Sara will share with us relevant insights on student membership and benefits with us. With that, I ask you to give your full attention to Sara as she walks us through. Sara, you're welcome.
Thank you so much, Kevin, for that introduction. I'm going to go ahead and share my screen. I'm going to share with you guys a little bit of information about our benefits and resources available for students in APS. As Kevin mentioned, I am the coordinator for the APS Student Ambassadors Program, and I also work on other membership and benefits programs for the organization. So APS offers a lot of unique benefits to our members in order to better serve the broader physics community. And we let you stay current on what's happening in physics with access to the Physics Today magazine, our APS news, and also our various online publications, and over 20 different meetings throughout the year, with also discounted meeting rates for members. Is my screen sharing properly?
It is.
Okay. Sorry, I wanted to double check because my little border disappeared. Anyway, so APS also helps you take advantage of our networking opportunities offered through involvement with our special interest groups known as APS units, which are matched to your fields of interest. You can network with like-minded colleagues and peers through our online forums hosted through APS Engage, attending our meetings, or also volunteering with APS units or our society level committees. By getting involved with APS, you help create a stronger physics community by adding your voice to those of 50,000 of your colleagues. APS can be an advocate for funding for research, science education, and provides scientific expertise on issues such as energy and the environment. Members of the community benefit from a lot of education, diversity, and public engagement programs that we offer as well. There's a lot of opportunity for professional development and recognition through APS, either by attending and presenting at our APS meetings, submitting your papers to our APS journals, or being recognized by peers and colleagues through APS awards, many of which are specifically designed to award students. We also offer valuable career information via meetings, our APS Careers website, which I'll touch on a little later, and also our APS News publication. You can learn more about our benefits as well as reciprocal arrangements with physics societies around the world, and our discounted and free rates for students at aps.org/membership/benefits. Hello, slide. There we go. So students do make up a huge part of the APS community. Currently, about 35% of our membership is students. So in addition to all the standard benefits for our members, we also offer a lot of unique opportunities for students to support this growing group of our membership. With APS, you can really start preparing for your future by building up a network of like-minded individuals around you, as well as mentors and the resources you'll need to excel in your career. One of our most prominent resources is the APS Careers website, found at aps.org/careers. In addition to the APS job board, where you can find current physics job listings, these are just a few of the many resources available. You can sign up for our Career Shape Up series, which sends tips, resources, and fun challenges to help you achieve your career goals. We have our APS Webinars program, which connects you with the expertise of individuals who can offer insight into physics careers, educational programs, and also professional development for students working in physics. There's also a repository of all of our past webinars that you can view in case you miss any. You can find lots of resources for job seekers, including the employment resources for international members, under the career guidance section of the Career Center. And you can also see the wealth of opportunities for physics graduates in industry, national labs, and more by getting the guidance you need through the Careers 2022 guide. So there's lots more to explore on the website. I do encourage you to go online and check these out. We offer, in addition to these career services, one-on-one mentoring opportunities for students and early career scientists. So the national mentoring community operates under the vision that every student from a marginalized ethnic or racial group who's interested in physics has access to qualified mentors, opportunities, connections, professional development, peer support, and the resources they need to succeed. Our APS Industry Mentoring for Physics program, also called IMPACT, connects students and early career scientists from any country with industrial physicists worldwide for the purpose of providing career advice. In this era of globalization, our international issues span across essentially all aspects of APS and the physics community. So the APS Office of International Affairs works to connect global members with programs and resources as well. Some of these include the International Engagement Around the World tool. So you can find programs and opportunities available within your country or region. There's tons listed out there. Please check it out. The African Physics Newsletter, which highlights news and research of physicists in Africa, along with upcoming events. And our task force report on expanding international engagement to improve how APS engages and serves our international members. They offer many more on their website at aps.org/programs/international. One of our greatest benefits for students is our travel funding opportunities. These are many opportunities specific for students to fund meeting registrations and, when allowed, travel to APS meetings as well. There's over $200,000 available per year for student funding through our APS units. So as mentioned, those special interest groups, make sure you're checking those out, getting involved, so you can see when these awards are available. And remember to apply for any award as early as possible. A lot of these awards are decided months before the meetings actually occur, so you want to really be on top of that. But you can see a list of all the award opportunities on the APS website at go.aps.org/unit_travel. And finally, I've just outlined a few of APS's programs and opportunities, but you can find a lot more information at aps.org/programs about all of our different support resources. We have government affairs, innovation, education, women in physics, industrial physics, public engagement, and much more. So please do visit that website, aps.org/programs, and check out all that APS has to offer. If you would like to join and are not already a member, visit aps.org/membership. And please do contact us at membership@aps.org if you have any questions or issues. We are more than happy to help. And do not forget that any student can receive their first year of APS completely free. So be sure to sign up for that 1-year free trial to see what you can get out of an APS membership. I'm going to go ahead and stop there and hand it back over to Kevin. Kevin, thank you again for letting me share this information. Please, again, reach out to us if you have any questions about APS memberships, or reach out to Kevin as the APS student ambassador. He likes to touch base with students all over.
Definitely. Thank you very much, Sarah, for this presentation. We're most grateful. And so I believe that from here, people who are not members at the moment will head to www.aps.org/membership to enjoy the 1-year free trial. Thank you, Sarah. So next on the list, as I think the part that most people have been waiting for, that will do a very brief introduction of our speaker before we commence. But I think I have a question here from Kofi concerning APS membership. We have some more time to ask Sarah that. She say, I think Kofi says that are there mentors available to help in applying for scholarships in university outside your country? Sarah, any answer with regards to that?
If you do have questions for applying for scholarships, any mentor you're paired with, I'm sure could help you with that. In particular, if you reach out to our Office of International Affairs, they can provide a little more insight on connecting with universities outside your current country.
Okay, thank you, Sarah, for that response. I believe it was clear to Kofi. If we have any more questions, you can put them in the comment section and I'll direct them to Sarah. But then if we don't have any, I think we can move ahead with the introduction of our guest speaker. Yes, as tonight we have Michel van Biezen. Michel van Biezen is a professor of physics based in the US, having been an adjunct professor of physics at Loyola Marymount University, El Camino College, Santa Monica College. He has lectured numerous courses scattered across physics, astronomy, and high mathematics. Professor Biezen has undertaken extensive research projects in global warming and cosmology. As an engineering manager at Raytheon Company, he has developed radar tactical software for the Grumman F-14 Tomcat, the McDonnell Douglas F-15 Eagle, and the McDonnell Douglas F-A-18 Hornet aircraft. At Raytheon, he has been instrumental in improving circuit board manufacturing techniques in circuit board manufacturing while analyzing GPS performance. Together with his wife, he has made over 9,000 educational YouTube videos in physics, chemistry, astronomy, mathematics, mechanical engineering, electrical engineering, GPS, and Kalman filtering. And these videos have been extremely useful to many students across the globe. I believe many of us here will testify to that, even including myself. Listen, I think I started watching Professor's videos at the age of 14, as I still remember the very first video I watched of him on quadratic equations, if Prof will recall. In fact, Prof he's competed in track and field, cross-country soccer, swimming, and water polo games. And he has also coached track and field, as well as refereed over 1,000 soccer games. Tonight, I urge you to make yourselves comfortable and be ready to learn something. In the course of Prof's lecture or presentation, if you have a question, just put it in the comment section and I'll do well to put them before Prof when he's done. Dear participants, you're welcome to our lecture online. Prof, you're welcome.
All right, Kevin, thank you very much for the introduction and thank you very much for inviting me. It was a lot of fun last time and hope we'll have fun again today. Also, I must thank you for all the work that you've put into it. It must be an enormous amount of work, and also for Sara helping and introducing everyone to the APS concept. It's a very good organization and it's very beneficial to the students who join that organization. So I'm very glad to be able to be part of it by giving you this presentation. So the presentation today is astronomy and beyond, or the universe and beyond. That's a good way to put it. And I think we'll have a lot of fun. So I decided not to present view graphs. There's so many beautiful pictures I could have shown, but I don't think that's the purpose of today's talk. Today's talk, I want to bring you into a virtual understanding of our universe in a way that you may have never heard before. And most of us don't have a lot of time during our daily lives, especially when you're students, you're busy studying for exams, trying to get your homework done, working, all those things that involve life. And not very often do we stop and pause and look up at the sky at night and wonder what's out there and why are we here and what's the meaning of everything. And so I'm trying to give you some insight into those particular questions. So the universe, as far as we know, started about 13.5 billion years ago. And when the universe first unfolded from, of course, no one really knows how, but we imagine that something like a Big Bang happened. And shortly after that, the universe primarily consisted of two elements on the periodic table, hydrogen and helium. And obviously, everybody knows that the Earth is made out of a lot more elements than just those two. Our bodies are made up of many more elements than those two. And you may wonder, well, where did the elements come from that make up the Earth? Where do the elements come from that make up our body? They didn't exist when the universe first existed 13 billion years ago. So some of us might have heard, well, aren't we made out of stardust? And in essence, that is correct. But what does that really mean? Because if you take a typical star, like our sun is maybe slightly bigger than a typical star, but it's in all respects a very normal star. What stars end up doing is, first of all, they are formed out of a big cloud of dust and gas, primarily hydrogen and helium. And through the action of gravity over many, many millions of years, they slowly come together. And as they begin to form a more dense clump of that gas, well, then the pressure of that compression, of that gravitational compression, begins to heat up the star at the center. And as this continues, the pressure will continue, the temperature in the inside of the star will continue. And eventually, when enough pressure is built up, because if there was nothing to combat that, the star, because of gravity, would just continue to compress into a smaller volume. All stars go through that initial birth process, as we call it. And eventually, the temperature at the very center of the star will reach a magical temperature of about 10 million degrees. Once the star reaches that temperature at its core, the temperature is sufficient to make the atoms move at sufficient amount of speed so that the hydrogen, as the hydrogen comes together and is on a collision course, the enormous repulsive forces can actually be overcome by the enormous speed they will collide. And through that process, you'll have what we call fusion, nuclear fusion at the center of the star. And slowly over time, hydrogen is then converted to helium. In our sun, that process will take about 10 billion years. We're about halfway through that process. And towards the end of that process, when the star has filled its core with helium, well, then that process will stop, because then the temperature is not sufficient to keep the process going. And besides, all the hydrogen in the core is now being converted to helium. The star, like the sun, will convert roughly 600 billion tons of hydrogen into helium every single second. And a small amount of that will be converted into energy via the famous equation E equals mc squared, the equation that Einstein discovered. So that is where the sun's energy comes from this regular process where hydrogen is being slammed together and converted to helium. It's called the proton-proton chain, where slowly hydrogen is then converted to helium. But when this process is done after 10 billion years, and no one needs to worry, we have another 4 or 5 billion years to go before that process is coming to an end. So we'll have the sun's rays keeping us warm for a very long time. But one day that process will end. And then the core will begin to collapse, because then there's nothing to prevent the gravitational forces, which are enormous, to compress that core. But as that core is being compressed, the temperature will again begin to rise. And eventually, as the core temperature reaches 100 million degrees, then the next fusion process begins, where helium is now converted into carbon. Now, we know that we are made out of carbon. That's not primarily, but it's definitely a big part of our bodies. There's a lot of carbon around the world. So finally, we begin to realize, oh, the next element being formed inside stars is carbon. And so when slowly over time at these enormous temperatures, the core fills up with carbon when helium is converted to carbon. Now that process goes a lot faster because the temperatures are so enormous, the pressures are so enormous that this process only takes maybe about 50 million years. Of course, when I say only 50 million years, that's still an enormous amount of time. But compared to 10 billion years, that's a very short period of time. And eventually the entire core will be filled with carbon. And then that nuclear fusion process will stop, the core will begin to collapse again, and then the temperatures continue to rise once more. But with the vast majority of the stars, with more than 99% of all the stars, that's where the process stops, because there's not enough gravity and there's not enough matter to push the core to the enormous temperatures required to continue that fusion process. And eventually the compression will stop and we'll have a big ball of carbon. Now, the reason why that compression stops is because within that core is now a big ball of carbon, essentially. Within that core, we have a lot of free electrons because at these high temperatures, of course, all the elements have been completely ionized and all the electrons are floating within the very dense packed nuclei. And those electrons, they repel each other. They repel each other with an enormous amount of force. And the repulsive forces between those electrons eventually stops the compression of the core, preventing it from reaching the temperatures necessary to reach the next fusion temperature required to continue fusing it into heavier and heavier elements. So the outer layers tend to be shed off, and then what's left is what we call a white dwarf. And so we now have the enormous core of a star compressed to the size roughly of the Earth. So white dwarfs are no bigger than the Earth. They are enormously hot when that process stops, but not hot enough to continue the fusion process. And here we have this big ball of carbon, which of course cannot be utilized for our bodies because we can't just pull the carbon off that white dwarf. So again, where did the carbon come from that makes up our bodies? Where does all the elements, the silicon and the oxygen and the iron and everything else that makes up the Earth, where did all that come from? Well, it turns out that there's one specific star that is able to produce those elements. But before I get into that part of the story, let's go back and think about these repulsive forces of the electrons, because that's something that's really underappreciated. Something is strong enough. The repulsive forces, by the way, we call that the electron degeneracy, but those repulsive forces between the electrons are so absolutely enormous that they prevent the core of this enormous star to collapse in on itself. We talk about an equivalent mass of potentially 100,000 Earths packed together into a volume no bigger than a single Earth. And yet somehow these repulsive forces prevent the star from collapsing further. So I thought of an interesting thought experiment. Let's say for a moment that we have 1 gram of hydrogen. So how much would 1 gram of hydrogen be? Well, if you compact it into a space this big, that would be about 1 gram of hydrogen. And of course, the vast majority of the mass of the hydrogen is in the nucleus. So if we could somehow separate the electrons from the protons of 1 mole, 1 gram of hydrogen, and we take all those electrons, which is 1 mole of electrons, and split it into 2 little boxes. So half a mole is in one box, the other half a mole is in the other box. We close the lid, we tie it tightly so the electrons can't come out. Of course, we can't physically do that because it'd be obviously way too difficult. But if you could just go with the story a little bit. And then let's weld that little box to a steel beam. And the other little box with the other half a mole to another steel beam and place the 2 beams on top of each other. Now those 2 little boxes with a small fraction of a gram of electrons in them, a half a mole in one box and half a mole in the other box, are now attached to those 2 beams. And of course, they will repel each other and they will lift the beams apart from each other. What would it take to keep the beams about 10 centimeters apart? Because the force of repulsion between those small fractions of a gram of electrons are actually absolutely enormous. The steel beams themselves are not heavy enough to prevent them from being pushed apart. So how do you keep the beams a distance of 10 centimeters apart? So let's put some elephants on top of the top beam to weigh it down. Now the question is, how many elephants would it take to keep the two beams from flying apart from another by these repulsive forces of these electrons? So I got onto my calculator, I calculated it, and I redid the calculation about 4 or 5 times just to make sure I didn't make a mistake. It turns out it would take 40,000 trillion elephants on the top beam to keep it from being pushed away from the bottom beam, because those two little boxes filled with a half mole of electrons each. 40,000 trillion elephants necessary, the weight of those elephants, to keep the beams from being pushed apart. Wow. So the forces in nature, the electrical forces, are absolutely enormous, and they're needed to create all the various things that we have, stars and planets and our bodies and everything else. So now let's go back to that big star. About 1 in 1,000 stars are very big, much bigger than the sun. Those stars are so enormous, typically at least 8 times the mass of the sun, that when they go through this nuclear fusion process, and because they're so much bigger and there's so much gravitational force, the temperatures end up getting much hotter. And so the nuclear fusion process goes very quickly. They burn through their hydrogen probably in a matter of 50 million years. They burn through their helium in probably less than 10 million years. And then when their core fills with carbon, there's so much mass, so much weight in that core that the force of gravity continues to press down on it and gets the core to be hot enough, at least 500 million degrees, to continue the process. And so then we start fusing nitrogen and oxygen and neon, and all the next elements in the periodic table are continually being fused by this enormous pressure and this enormous temperature. Eventually, the core will reach the point where everything turns into iron. And iron is an extremely interesting element, is an extremely unique element on the periodic table. Each time that a star fuses something into its next heavier element, it produces energy. It takes some of the mass and converts it into energy. But by the time we get to iron, when you try to fuse iron into its next element, such as cobalt or nickel, something strange happens. Instead of giving off energy when iron is fused into nickel or cobalt, it absorbs energy. You can no longer produce energy by then fusing iron into its next heavier element. And there's the problem. As the core begins to fuse iron into cobalt and nickel, instead of giving off energy, it grabs energy out of the core and starts reducing the radiated pressure, and the core begins to collapse. And as it collapses, the temperature goes up. It continues to fuse more iron into cobalt and nickel, but again, energy is pulled out of the core. And all of a sudden, in a matter of just seconds, the core begins to collapse. And as it collapses into a huge rebound where the temperatures are so high that an explosive event causes all the other elements of the periodic table to be fused in that very short few seconds. So then you end up with this massive explosion. It's called a type 2 supernova. And it's in this particular explosion that all the elements of the periodic table are created and blown into space. That is the beginning of where all the elements that make up our body and the Earth come from. Now, of course, they're blowing into space and they float off and they begin to mingle with other nebulas. Again, under the conditions where nebulas turn into stars, and that usually happens under 3 potential conditions. One condition is that an explosion will compress the gas sufficiently where gravity will overcome the pressure of the nebula and turn itself into a star. Or 2 nebulas could collide, or we could have a very bright star shining ultraviolet radiation on a molecular cloud and cause that to collapse into a star. But through one of these processes, stars do form continuously. And so all over our galaxy, new stars are being born all the time through this process. But this time, about 4.5 billion years ago, where we are today, one of those massive stars exploded into type 2 supernova. And the remnants were collected together with the available hydrogen and helium clouds that were around it. The pressure from the explosion would have collapsed one of those clouds. And from that, a new star was formed, hence our sun was formed that way. And not just our sun, also the solar system because typically there is this rotational motion, and as things collapse because of the conservation of angular momentum, the whole mass of debris that came from the explosion, coupled with all the helium and hydrogen gas that's within that cloud, begins to rotate faster and faster and faster and spreads this out into a disc-like structure. At the center, enough mass comes together and forms the protostar that eventually then becomes the real star like our sun. Around it, you'll have this disk of material that swirls around it. And it's from this disk of material, which is now interlaced with all the elements of the periodic table, will slowly coalesce together into chunks and then boulders and then bigger chunks and eventually into shapes like the asteroid belt. And eventually, as these coalesce together, the planets are slowly begin to form within that disk of debris around the protostar. In the meanwhile, the protostar will continue to collapse in on itself. And as it does, because of gravity, the temperature of the core begins to increase more and more and more. And eventually, it gets to the point where the temperature of the core reaches 10 million degrees, the fusion process starts, and there a new star is born. That's how our sun formed about 4.5 billion years ago. But unlike many stars around us, the sun also, as well as the debris field around the sun, contain these heavier elements. And so, in the inside of the emerging solar system, we ended up with 4 terrestrial planets that you can walk on, that have rock and metal within them. Turns out the Earth is about half metal by mass, so the core of the Earth is primarily metal and primarily iron. That element that caused the type 2 supernova to explode is now contained within the Earth, as well as Mars, Mercury, and Venus. As the sun emerged and began to shine strongly throughout our solar system, the heat of the sun's ray and the pressure, the radiation pressure of the sunshine and the solar wind particles, as we call them, pushed all the light elements away from the inner part of the solar system, but the heavy materials, such as the rocks and the metals, they stayed behind because they're not as easily driven off. And so in the inner solar system, we ended up with the 4 terrestrial planets and the asteroid belt. But much of the gas and the water vapor, because at temperatures as high as they were around the sun, they were driven off into the outer solar system where the huge gas planets were formed, because primarily that's where most of the gas resided in our solar system after the solar wind and after the solar radiation pushed everything out. Initially, when the Earth was formed, it did not have any water to speak of. So it was just a barren, hot cinder of hot rock that slowly started to cool down over time. But in the far reaches of our solar system, billions and billions of pound comets were forming from the coalition of the water vapor that had then refrozen out there past what we call the frost line. And those comets, of course, they circled the solar system just like all the planets do around the sun. But because of the internal gravitational interaction between those billions and billions of comets, some of them were kind of driven into a different path and started their path inward towards the inner solar system. And just like sometimes you'll see what we call the comets coming by the Earth around the sun and back out into space, well, those comets have been doing that for the last 4.5 billion years, and there were a lot more of them back then. And many of those comets ended up colliding with the Earth, as well with the other planets, and slowly the amount of water that we currently have in our oceans will build up by the collisions of millions upon millions of these comets that have been hitting the Earth, especially during the initial 500 million to 1 billion years after the solar system was formed. But there's the answer to the question, where did the elements come from that make up our bodies and make up the Earth? Well, they came from that supernova explosion. If it wasn't for that supernova explosion, we wouldn't exist. The elements that make up our bodies, that make up the Earth, simply wouldn't have existed. It would have just been hydrogen and helium. So we have our lives, in a sense, to thank to that 4.5 billion years ago super explosion that occurred in our neighborhood. Now we live on a planet that's quite unique. The Earth is perfect for life, although obviously there's sometimes storms and things like that make it very unpleasant. But by and large, the Earth is just an amazing planet. It is just large enough so that the gravitational attraction prevents the atmosphere from escaping like it did on Mercury and like it almost completed on Mars. We also have something to protect us. We have a magnetic field. The core of the Earth is to some extent solid, some extent liquid, and that moving mass of metal material that churns around causes a dynamo effect that puts a nice protective blanket of magnetic field around us that protects us from the solar wind that otherwise would destroy all life on Earth. We also have an ozone layer around the Earth that protects us from the UV radiation that we get from the sun. Without that ozone layer, life would be virtually impossible. We also have the Earth primarily covered by oceans, which tremendously temper the climate and the temperature and keep it very nice. Water has tremendous qualities that it can contain an enormous amount of heat, making it cooler in the summer and warm in the winter. Also, of course, water is absolutely necessary for life. Not only that, the Earth also has the oxygen in the atmosphere, which is very unique. And the oxygen, of course, came from a process called photosynthesis that developed early on in the life on the Earth. So we live on a planet that has these absolutely amazing properties that are hard to find. How hard is it to find a planet like Earth? Well, so far we've already discovered thousands, at least 4,000 extrasolar planets, not by direct observation of photographs because they're so small and so far away. Eventually we'll be able to do that. But we can figure out there's planets there because of the effect on the motion of the stars that they go around. And we can also find it from the effect that it has when sometimes they go in front of the star and block out part of the light of the star. So we're able to figure out from various means of observation that there's at least 4,000 planets around stars in our neighborhood. And of course, that's just in our little neighborhood. If you go throughout the entire galaxy and entire universe, there's of course billions upon billions of planets. But of all those thousands of planets that we've discovered to date, only a small percentage, about 4%, are deemed to be terrestrial planets. The vast majority of planets we find are gas planets. They're not very hospitable to life. And of those 4%, only a very small fraction of those actually reside around a star and has the conditions available so that life potential could be possible. So we haven't found a lot of planets yet. Of course, we're still trying, but we haven't found a lot of planets yet that seems to be able to support life. So we live on a very, very special planet in this neighborhood of our galaxy. Talking about galaxies, well, we live in the galaxy called the Milky Way galaxy. And the Milky Way galaxy contains about 250 billion stars. Some are bigger than the sun, quite a few are smaller than the sun, but 250 billion of them. And it's kind of hard to imagine what 250 billion is. So I tried to think of a way to express that. And so I brought my little marble here. The little marble is about 1 centimeter across. Let's assume that we had a box that's 1 meter cube, 1 meter wide, 1 meter long, and 1 meter high, 1 cubic meter. You could fit about 1 million of these marbles in one of those boxes. Well, how many of those boxes would you need to make up the number of stars in our galaxy? You would need 250,000 of those 1 cubic meter boxes filled with 1 million marbles each, if those were representative of the number of stars in our galaxy. 250,000 boxes filled with 1 million marbles each. That's how many stars there are in our Milky Way galaxy. Our Milky Way galaxy is absolutely huge. And another way to kind of get a feel for how big our Milky Way galaxy is, I brought along 2 ping pong balls. Now let's assume that this is the sun and this is the next nearest star, Alpha Centauri. Alpha Centauri is about 4.5 light years away from us. But let's say that we could shrink those 2 stars down to this size. They're about equal in size, Alpha Centauri and the sun. And let's assume that we can shrink them down to this size. Then how far apart would those 2 stars be at this scale? Well, you might think maybe a football field away, maybe 5 football fields away. Well, it turns out that if this was the sun at this size, and you want to, at the same scale, put this star, Alpha Centauri, at a distance away from the sun, it would be about 1,000 miles away. 1,000 miles is 1,600 kilometers. Imagine Two stars this size at a distance of 1,600 kilometers, and that is the distance between our sun and the next nearest star. It's about 40 trillion kilometers. That's an enormous distance. And yet, when you look at a galaxy, you see it as a conglomerate of a massive quantity of stars that almost seems right on top of each other, but in actuality, they're quite far apart. Now, of course, in the nucleus, they're a little bit closer together, but we live in one of the spiral arms of the galaxy, and there the stars are somewhat a little bit further spread apart. But yet, 250 billion stars packed together into a conglomerate called a galaxy, where the stars are like 1,000 miles apart when they're down to this scale. So, excuse me for one moment. I have a dog nearby, and he was biting himself, so I have to tell him to stop. All right, so where were we? So we're talking about the size of the galaxy. So our galaxy is 100,000 light years apart, or I should say in diameter, and we live about 28,000 light years away from the center. But again, when you think about 28,000, 100,000 light years, what does that really mean? It's kind of hard to put your mind to that and to try to really appreciate the size, but let me try it this way. We know that the speed of light is 300,000 kilometers per second. Every 1 second, light travels 300,000 kilometers, which is 7.5 times around the world, for example. Of course, light doesn't go around the world, but if it could, it would do that 7.5 times in 1 second. Now, 100,000 light years is the distance that light will travel in 100,000 years. Now imagine second after second after second. Each second in our lives, light travels 300,000 kilometers. In 10 seconds, that's 3 million kilometers. In 100 seconds, that's 30 million kilometers. And it just continues like that. Imagine a whole day, 86,400 seconds. Each second, 300,000 kilometers. Now multiply that times 365, that gives you a year. How far does light travel in a year? And yet the galaxy is so enormous that light takes 100,000 years to travel from one end to the other end. Imagine 100,000 years, 1 second at a time. A lifetime is just a smidgen of that, but a lifetime is a long period of time. And all this time, light is traveling and traveling and traveling. And yet, how many lifetimes would it take for light to reach the other side of the galaxy? Galaxies are absolutely enormous. And how many galaxies are there in our universe? Well, our best estimate at this time is that there's about 200 billion of those galaxies in our universe. Some are smaller than our Milky Way galaxy, and some are bigger. Some are absolutely enormous. But the fact that there's probably over 200 billion galaxies in the universe, and that's the visible universe, it's just mind-boggling. And to get a feel for that is, where are our neighbors? Now, we do have a few galaxies. I think there's about 3 of them that revolve around our galaxy, that are gravitationally captured by our galaxy because it's a bigger galaxy, and they go revolve around our galaxy. But the next neighbor that's kind of like ours is called the Andromeda galaxy. It's about the same size, maybe slightly bigger than our Milky Way galaxy. And that galaxy is about 2.2 million light years away from us. So imagine the galaxy being about this big, the Andromeda galaxy being about this big, and then the distance between them would be about 22 times this distance, with this vast amount of space in between the two galaxies. Light from the Andromeda galaxy takes 2.2 million years to get to us. Imagine 2.2 million years. That's a time frame that's almost unimaginable. And yet that's how long it takes for light to travel from our nearest big neighbor to us, 2.2 million years. And to get an appreciation for that, let's imagine that we could somehow snatch away the Andromeda galaxy, just magically, instantly, just make it go away. What will we see? Well, it turns out nothing. We'd look up in the sky and it still would be there. Even though it's no longer there, it still appears to us because, well, it would take 2.2 million years before the last rays that left the galaxy would have reached us. So we wouldn't even know that the galaxy was no longer there for 2.2 million years. But then once 2.2 million years are gone, would the galaxy just suddenly disappear? And the answer is no, because the galaxy is 100,000 light years across, which means that slowly the light from the front of the galaxy would no longer appear to us. And slowly over time, the galaxy would slowly fade away. But how slow? Well, in a period of 1,000 years, only about 1% of the galaxy would no longer be visible. The other 99% of the galaxy would still be visible to us. It would take an entire 100,000 years for the whole galaxy to suddenly fade away from our vision. Excuse me, I need something to drink here. It would take 100,000 years for the galaxy to slowly fade away. Can you imagine that? Even though it was instantly made to disappear, it would take 2.2 million years before we realize it's no longer there. And not only because we start seeing very small portions of the galaxy to slowly disappear over time. Our universe, our galaxies, the distances between them are absolutely enormous. So here we have discovered, of course, we haven't counted them all, that would take an enormous amount of time, but from taking photographs into deep space in various locations, we've been able to surmise that there's at least 200 billion galaxies in the visible part of the universe. Now, what do we mean by the visible part? Well, since our universe is only about 13.5 billion years old, and it takes light a long time to travel in very large distances, if we pick a point 13 billion light years away, it would have taken light 13 billion years to reach us. So a galaxy 13 billion years ago, that light would take 13 billion years to reach us. But what if there was a galaxy 14 billion light years away from us? Well, that light will not arrive for another 500 million years, so we'd have to stick around and read the newspaper for a while until the light would finally reach us. And our estimate is that there's way more galaxies beyond the visible limit of our universe than there is within the visible part of our universe. Our universe probably goes out way further than we're able to see. But again, those are theories. We have good reason to believe they're there, but we'll never, in our lifetimes, of course, be able to see them. We live in this enormously humongous universe with hundreds of billions of galaxies, and each galaxy being an entire universe on its own, where light will take 100,000 years to travel across it. But there's even things out there that are more mysterious than the size and the complexity of the universe. Think about time. What is time? Well, time separates the past from the present from the future, and time always seems to move forward. Whatever we experienced yesterday is in the past. Whatever we will experience tomorrow is yet to come. And right now we're in today. And it doesn't seem possible to travel to tomorrow and come back, or to travel to yesterday and come back. We can do that in science fiction movies, but not in real life. But is time an absolute? Does time always move at the exact same speed? And the answer is no. It turns out that time is affected by gravity. Well, gravity is actually an effect of the bending of space. And he said, well, space, how can space bend? Space is nothing, the nothingness, the vacuum of space. And true, we talk about the vacuum of space, and that means there's no atoms in space, although that's not entirely true either. There are some atoms in space, and in those atoms are they're very far apart from one another, but they're still there, but they're so rarefied that we assume it's like a vacuum. Okay? But what is space itself? Is space just absolutely nothing, or is there something to space? And you might have heard the term the fabric of space. And there's a reason why that term exists, because space is not the nothingness that we thought it was. Space is actually something, although we don't quite know yet what it is. But space can actually be deformed, and space is also allowing time to move forward. So if you take an object like a star and you place it in space, you bend or warp space around it. Now, we can't really imagine what that looks like because we're used to a three-dimensional world and a three-dimensional universe. So how does something bend into, let's say, a four-dimensional thing? We don't know how to explain that. But what we do know is that when you place another object in that warp of space, that object will then fall towards the bigger object. Like if the Earth stopped revolving around the sun, we would just simply go and crash into the sun. Because there's this warp around the sun that the Earth will fall into. The Earth makes its own warp, and the moon would fall into the Earth if the moon was not revolving around the Earth. So space is bent around every object. Anytime you put mass in space, it causes something to space to cause things to fall into it, and that is the effect that we know is gravity. And another way to realize that space is bent is, well, that was proven by Einstein in 1919, because he's the one that came up with that concept. And of course, nobody believed him. And he said, I can prove it to you. And in 1919, there was going to be a solar eclipse. And Einstein told everybody, take pictures of the sky 6 months before the solar eclipse. And the reason why you want to do that is because if the Earth is going to be over here in 6 months, then 6 months earlier, the Earth is going to be on the other side. That means you can see the sky on this side, but 6 months later, you're not going to be able to see the stars in the sky on this side because it's daytime. You can only see those at night. But when the Earth is on this side and there's a total solar eclipse, it blocks the light from the sun, and for a few minutes, we can see the stars in the sky. So we said, take a picture of those stars 6 months earlier when the sun is on this side, and when the Earth is on this side of the sun, and then compare that to the picture you will be taking when we have a total solar eclipse. And he said the stars will not be in the same place because the light from the stars, as they pass the sun, well, that light will be bent in that warp of space, proving space is warped. So nobody believed them, but they thought it was going to be a fun experiment, and they loaded up a boat. They brought a lot of spirits and wine and beer along with them, and they had a great time for about 30 days traveling to the spot in front of South America off the coast where that total solar eclipse is going to happen. And sure enough, they took pictures, they compared them, and the stars had actually displaced themselves because the effect of the light that caused the stars to appear to be in a different location than they actually were, and actually predicted how much they would have moved, and it was absolutely correct. So he proved that space around stars does warp, and that's the warp that causes the force of gravity. But what else happens in that warp is that time actually slows down in a gravitational field. How much? Not a lot, but enough for us to be able to measure. For example, when you think of GPS satellites, well, they're about 20,000 or so kilometers above the surface of the Earth, and gravity is a lot less high up compared to being on the surface of the Earth, which means that time runs slower on the Earth because the gravitational field is strong. I have to think about that for a moment, but time runs slower on the surface of the Earth compared to the time in the satellites. And so the clocks in the satellites, well, they get ahead because time is slower here. So the time between the time on the satellites and time on the Earth will not be the same as time goes by. It differs by 45 microseconds per day. You may not think that's a lot, but for satellites, that's an enormous amount because light travels about 30 centimeters per nanosecond. So 45 microseconds, well, now you're talking about being like 15, 20 kilometers off from where you thought you were. So we have to account for that time difference. Otherwise, our GPS satellites and our GPS devices wouldn't work. Time slows down in a stronger gravitational field. So when you're not in a gravitational field, time runs normal, but inside a gravitational field, it slows down. Now, if you go to places where the gravitational field is stronger, such as the surface of a white dwarf, time slows down even more. Or the surface of a neutron star, time slows down enormous amounts. What about near a black hole? Once you reach what we call event horizon of a black hole, time will actually come to a stop. Time depends upon space, and the more space warps because of gravitational effects, the more time slows down. So time isn't absolute. If you were able to go to the event horizon of a black hole on vacation, stay there for a while, come back, you will not have aged a single day. Of course, That's not even possible because you would just get pulled into the black hole. That would be the end of you. But if you could, that would be an interesting experience because time would not move forward. That's not the only reason why time is not the same everywhere. Time can also be affected by the speed at which you move through space. And again, that's where space is a very special thing. Traveling through space does something to time. If you jump in a spaceship and you travel at near the speed of light, time for you will travel or will go forward slower than for the people left behind on the Earth. For example, let's say you have two twins and they're both 20 years old. And one twin was a little bit more adventurous than the other twin and decided, I want to become an astronaut. And by the way, there's this mission to travel to another star 15 light years away. And we have a special rocket that can fly at 99% the speed of light. So one of the two twins signs up for that mission, gets on the spaceship blasts off and travels to the star and to the planet near the star, excuse me, 15 light years away. Now, of course, for the person on the Earth looking at that spaceship travel to that other star, well, that voyage will take 15 years. And the twin left on the Earth will be 15 years older by the time the twin have reached the other planet, and then maybe spent a month or so at the planet, then comes back. And so the twin on the Earth will now be 50 years old because it was 15 light years to the planet, 15 light years to come back. It took about 15 years to get there, 15 years to come back. The twin left on the Earth would now be 50 years old. But the twin in the spaceship did not experience time the same way because traveling at 99% of the speed of light, time only moves forward at 1/7 the speed. And so therefore, the twin that went to the other planet came back will only have aged 4 years coming out of spaceship. That twin will be 24 years old, will only have lived and experienced 4 years of time passage, while the twin on the Earth will have experienced 30 years of time passage. Time is not absolute. Time depends on gravitational forces, and time depends, or essentially warping of space. And time depends upon how fast you move through space. Now you might think, well, what if I even go faster than that? Would I even age less? And the answer is yes. What if you go 99.9% speed of light? What if I went 99.99% speed of light? What if I could travel at the speed of light? Now, of course, we know that objects cannot travel at the speed of light. But then, of course, we're limited by what we know and understand. So let's say for a moment that we could. An object could travel at the speed of light. What would happen to time? Well, time would simply stop. Time would not move forward for you. And you could essentially travel across the entire universe in less than a blink of an eye. Time would not, you could travel from one end to the other of the universe, and time will not have passed a single second for you, not even a fraction of a second. Time would just stop. You'd be independent of time. Time would have no meaning because essentially you could do that a billion times back and forth and time would not go forward. So time is something we experience because we live in this universe and we're essentially prisoners of this space. But you can see that if we think far enough and we understand enough, we understand that time is not an absolute thing. Just an amazing concept. I wonder what it would be like to live in a universe where time doesn't exist. Could you travel forward and backwards in time? If there was such a thing as living in a place where time did not exist, could we go visit the past and visit the future? And that would be essentially the same time for you because time has no meaning. Things to think about. We live in an amazing universe. I got to quickly check to see if I was going to talk about some more things. So yeah, there were a couple more things I wanted to talk about. And one of them is gravitational lensing. What does that mean? Well, it turns out that if there's a galaxy far, far away, and then in front of that faraway galaxy, there's another galaxy. Remember already, when we put matter in space, it causes space to warp and bend. So the light coming from the faraway galaxy will approach the nearby galaxy, and because the warping in space, the light will bend around it and come back together on the other side when we see it. So we can actually see the galaxy behind the closer by galaxy, and normally we shouldn't be able to see it because it's completely blocked by the nearby galaxy, but yet we can see the image of that galaxy as it's bent around it. Now, normally we see little pieces of it on the side. It's not a complete image, but we'll see the top, the bottom, the left, and the right all coming together. And often that image has been amplified in size or magnified in size because it actually physically acts like a lens. That galaxy in between is if somebody put a big lens there, light goes through the lens, and of course everybody knows that a converging lens, as light goes through it, it bends around, comes back together, and depending upon where the object is and where the image is, it can be magnified, and in some cases magnified as much as 20 times. So it's kind of amazing that we see the effect of the bending of space through gravitational lensing as well. So trying to figure out what space is made of is actually being just a tremendous, interesting thing for me. Something I would like to study some more. Because when I think about it, what causes electromagnetic radiation, light or electromagnetic radiation, to travel through space? We know that for a wave to travel along a string, you have to have a string, you have to have a medium along which the energy of the wave can travel, because essentially waves is essentially energy that travels along a medium. So when you have a string and a wave travels along the string is the medium, and the energy of the wave can travel along the medium. If you have a water wave, well, you have the water, and the energy will travel along the water. So you can have ocean waves that travel for thousands of miles as they continue just through that medium. But what about light? Do we really believe that light can travel through space? And do we believe that space is nothing, just this emptiness, a vacuum of space with nothing, and light just travels through it? I don't see that as possible. You have to have a medium. Space essentially has to be a medium along which light and electromagnetic radiation can travel. Of course, you have the electric field oscillations, and then you have the perpendicular magnetic field oscillations. But for the electric field and magnetic field to oscillate, you have to have something along which it can oscillate, which is space. So space has properties. If we can combine all that knowledge, we can see how space has certain properties that allow E&M waves to travel. And by the way, E&M waves traveling through space is ubiquitous. It's everywhere around you. Continuously, E&M waves are traveling. Your body gives off electromagnetic radiation. The floor, your shoes, your hair, ice cubes in the freezer, every object in the universe is continuously radiating energy, and that energy travels through space. And you have to have space with certain properties to allow that to happen. And the fact that space allows light to travel at a specific speed that we know the speed of light is also part of its property. Maxwell figured out that the speed of light was equal to 1 over the square root of what we call the, I'm trying to think of the terms, of the permittivity and the permeability of free space. The properties that electric field and magnetic fields have moving through space, when you take those two constants in the equations that make up the equations describing electromagnetic fields, it's called the permittivity and the permeability of free space. If you take 1 over the square root of the product of those two, that is exactly equal to the speed of light. The speed of light is completely controlled by the properties of space. And if space had different properties, the speed of light would be a different quantity. And for some reason, that is the limit of what objects can travel at. Objects can never travel at or beyond the speed of light, only less than the speed of light. And so there's something about traveling through space. If you have an object and it travels faster and faster and faster. Now, we understand that there's kinetic energy, there's potential energy. When you lift an object up against gravity, you give it potential energy. When you make an object move, you give it kinetic energy. And the kinetic energy is proportional to the velocity squared. But that's okay for low velocities that we're used to in our everyday life. But what if we start moving at speeds close to the speed of light? There appears to be another form of kinetic energy, another form of momentum that has something to do with an object moving through space. it gains an additional form of energy that is not noticeable at normal speeds that we used to. But at speeds close to the speed of light, objects seem to gain an other form of energy. Now, you might have learned in the physics classes, in your relativity classes, that they say that mass increases. But there's plenty of scientists already realize that that's probably not even possible. It appears as if mass increases. We always talk about the rest mass and the relativistic mass that supposedly increases as objects go faster and faster. But it can be explained not necessarily by the increase in mass, but by the increase in another form of kinetic energy. And so once an object has gained this additional kinetic energy, if it then impacts on something, it will appear as a more massive object impacting. And of course, in our accelerators, we can do plenty of experiments that make it appear that particles that is being sped up to 99.999% of the speed of light act as if they're 1,000 times as massive as they were at rest. But just like an object hitting you at a high speed causes a lot more damage than an object hitting you at low speed, it makes it seem like you're being hit by a bigger object. Well, traveling at high speeds, you develop an additional amount of kinetic energy beyond the 1/2 mv squared that is tied to the properties of space. And in order to get things to move at that high speed, it takes an enormous amount of energy, just like it takes energy to get things to move in the first place to give them kinetic energy. So space is a very interesting commodity, interesting thing, interesting, whatever it is. It's hard for us to describe what space actually is, but definitely the concept of the fabric of space, because it's some strange thing that has all kinds of properties that will slow down time, that will cause gravity, that will make light bend. Yeah, it's a strange thing. And that allows electromagnetic radiation to travel through it, because if space was just an emptiness, and how could electromagnetic radiation travel through it? So there's still a lot of research to be done, a lot of things to be understood. And I would like to be part of that, because it really intrigues me to try to figure out what space is actually made out of. And further than that, what we also realize is that the universe is expanding. And it was Hubble who was able to make that relationship when he started observing with the new telescope that he was using here in the mountains above Pasadena. He began to realize that the farther galaxies were, the faster they appeared to be moving. And he found that there was a linear relationship. A galaxy that was twice as far away traveled twice as fast. A galaxy that was 3 times as far away traveled 3 times as fast. A galaxy that was 10 times as far away traveled 10 times as fast. The speed at which galaxies around us are moving away from us is linearly proportional to the distance away from us. It was so enormously linear that this could not be explained by some magic explosion that happened and everything was flying away from the explosion. It could only be explained if we assumed that the galaxies were stuck in space and space itself was expanding. And so therefore, the speed at which 2 galaxies move away from each other is simply proportional to the amount of space between them, because if space expands evenly everywhere, then we would see that kind of thing. And so this expansion of space is essentially an unfurling of space. It's not that the galaxies are moving away from each other, it's simply the galaxies are stuck within space. Now, they can move locally because there's gravitational attraction between galaxies, but the general movement of the entire universe is that they're all expanding, and the speed at which they expand from each other is proportional to the amount of space between them, because space itself is expanding. And for many years, especially in the early part of my career when I was teaching astronomy many, many years ago, I was telling my students incorrectly that we all thought that the expansion was slowing down. It had to slow down because the gravitational attraction of all the galaxies pulling at each other would cause this expansion to slow down. Just like when you throw a rock up, you expect it to come back down. When 2 galaxies are moving away from each other, you expect them to slow down because of gravity. But in the early 1990s, an amazing discovery was made, or maybe I'll go back, the late 1990s, I think it was around 1998. They discovered that supernova explosions, especially the type 1A, which all have the exact same luminosity when they explode, they appear to be dimmer than they should be when they were far away. They did a bunch of calculations, and the only conclusion they could come up with was that space expansion is accelerating. Somehow, that unfurling of space is going faster and faster and faster, and it's something that we cannot explain. So we have to come up with something. We came up with something called dark energy that pushes everything apart. Whatever it is, there's something mysterious going on. It could simply be that the property of space is such that it unfurls like a spring, and maybe that process is going faster and faster. Who knows? As you're adding more and more kinetic energy to the masses flying apart from each other. That's another thing I would like to explore a little bit more, because that may be the explanation. We don't know. That's what makes science so exciting, is that we have all these very intelligent people all over the world looking at these mysterious things and trying to come up with explanations. And vast majority of those explanations are wrong, and some of them are right. We just have to figure out which ones are wrong and which ones are right. But there's so much yet to be discovered, so much yet to be understood about the universe that we live in. So if you're going to go into the field of physics, astronomy, astrophysics, anything like that, mathematics, there's a lot of things to be discovered out there. And we need young minds to come in and take over from us old folks that eventually will no longer be around. We'll lay the groundwork on some things, and you take over and continue with the research and push it further away, push it further to the point of greater understanding. It's an exciting field, and yet we often don't even think about it because we're too concerned about our daily lives. And of course, that takes up the majority of what we do every day. But if you can just sometimes stop and think and stare up and look at the sky and wonder, what's it all about? How did our bodies come about? How did the earth come about? And when you realize the chain of events that must have happened for us to be here, it is absolutely miraculous. So I hope to have left you with something to think about. I know that I didn't use any fancy charts and beautiful pictures, but I'm hoping that in your mind, I was able to conjure up some thoughts so you can make up your own picture. It's my presentation.
Thank you very much, Professor. Thank you. I really learned a lot. But just before I go ahead, I think we have a couple of questions around. We'll try to take as much as possible. Okay, and so I have one that says that, can we create conditions for a black hole here in our world in order to see the beauty of time stopping? Is it possible for us to create the conditions that make for a black hole so that we can see the beauty of time?
Can we create it? And that is, of course, the big question, right? Is it possible? Some things are possible and some things are not. For example, we are trying to make nuclear fusion happen in a laboratory environment. And eventually we hope to do it at an industrial scale. So what we're trying to do there is create the conditions of the center of the sun where it's hot enough to get nuclear fusion to occur, and the energy produced would be absolutely enormous. If we ever manage to do that at industrial scale, our energy concerns would be over forever. But can we make a black hole? That we can't. A black hole is such an enormously destructive entity that can only come about when we have the forces necessary to push enormous amount of matter into a very small volume. And so that definitely is something we cannot do. Can we theorize that time changes? And the answer is yes. Can we then prove that it's so? And the answer is yes. We can measure it in smaller scales, such as the time dilation on GPS satellites is something we can actually measure, and we must correct for, by the way. Otherwise, our GPS satellites wouldn't do the job, and our receivers wouldn't know where we were. So we know that it's true, but coming up with something where we can actually make time stop, that is virtually impossible, unfortunately. Yeah, string theory. That's a good question. At this point, it's a theory. And also, I think a lot of people don't realize the strings that we're talking about are so small. For example, when you look at an atom, and then look at the nucleus of an atom, and then look at a string is so many orders of magnitude smaller than the nucleus of an atom that we'll never be able to see it and never be able to measure it. So it's a purely mathematical model. It's an interesting model. And yes, there are so many things we don't understand yet about the structure of matter, but we're starting to get into that. We're starting to get into understanding a little bit more about quarks and how quarks make up baryons. And so we are slowly beginning to, with our enormously powerful accelerators, we're able to slowly pull the secret veils away from understanding what material is made out of. But is it strings? We don't know. We may never know. But that's why we need smart people to come up with these theories to try and say, does this fit? And so now we go through the process of mathematically trying to describe how string theory would work and how it would explain the things that we're observing. And if it doesn't do that, then it cannot be proven. So we need to be able to show that the string theory shows that the observations match the theory, and we haven't been able to do that yet.
Oh, okay. Okay, that's fine, Prof. Thank you very much for that response. I think I have one more question here that says that time slows down means events in the physical world slow down. Then cesium-133 atoms fall and emit photons less frequently than usual. I think he wants to find out if his thought is right.
So that's a good question. Now, of course, the answer to that is take a look again at the GPS satellites. They do have atomic clocks on those satellites. Those atomic clocks are based upon the vibrations of the atoms, just like the example you gave. And we know that those vibrations change in frequency when they're on GPS satellites, and that's why the time dilation occurs, because the atomic clocks on the satellites do not run at the same speed as the atomic clocks left on the surface of the Earth. So we have a network of atomic clocks, about 400 atomic clocks around the world that together form the UTC time. And the satellites are then compared to that UTC time. And every day, because of the difference in the movement of time on the satellites compared to the Earth, they lose, they get ahead, right? Because it's slower on the Earth. So they get ahead 45 microseconds every day. So it actually physically affects every aspect of existence, including the vibrations of atoms, because of the dilation of time. So yes, everything is adjusted according to the time in that time frame.
Okay, thank you. I think we have some more questions here. Let's say, Professor, you said the speed of light is 3 by 10 to the power 8 meters per second. From astronomy, we know that the farther away the galaxies are, the faster they are moving. We know that the universe has no edge, and this means our universe is infinite. So in conclusion, in one moment in the future galaxies will be far enough to reach the speed of light. Is this true or not? I think I get what he's saying. Prof, is it clear to your end?
Yeah, I think I understand the question. So, the question is like this. Let's say we look in one direction, we look at the galaxies very, very far away from us, and we see them moving at enormous redshifts at speeds that are like close to 99% of the speed of light in one direction. And then we look in the other direction, we see those satellites move away at 99% of the speed from us. And so it would then appear that if you then compare the two galaxies to each other, that they would be moving away at roughly twice the speed of light. But if you could then go and travel to that faraway galaxy and then look back and see that other galaxy in the other end of the universe, which of course would not be possible. What if we could? We would not see that galaxy move at faster than the speed of light. So to an observer, we will never observe something moving faster than the speed of light. Now, are they moving apart from one another faster than the speed of light? And the answer then would be yes, right? So the physical distance between them would increase at a speed faster than the speed of light, but it would not be observed as such. And that's kind of, it's kind of a contradictory statement, but that's how it actually would be. So there's physically points away from us that move faster than the speed of light, but that's the difference is this. And again, I need to go back to the concept of space. it is the expansion of space that's causing them to move apart from one another. I believe that it's not possible to move through space faster than the speed of light. We will not be able to observe something moving faster than the speed of light, but physically they can move away from each other faster than the speed of light because it's caused by the expansion of space, not by the galaxies moving through space. That would not be possible.
Okay. Yes, I think I get it. So the speed of light being a barrier has to do with things that move through space, and not space itself expanded. The space itself may be expanded at a rate that is greater than the speed of light, but the things that move through it possibly could not move greater than the speed of light. That's fine, Prof. I get it. So when someone says, Professor, I have a question related to the age of the universe. What do you think about Hubble constant? Is it really a constant or not? Because if we want to measure the age of the universe by calculating it, then we have to take the inverse of this constant. But if this is a constant, then the age of our universe will always be the same. And after 1 million years, it definitely will make no sense.
Good question. So is the Hubble constant a constant? Well, let me tell you a little bit about Hubble constant. It is the most sought after constant in the world. We have spent more money trying to establish the value of that constant than of any other scientific endeavor we've ever done. Because it tells us so much. It tells us that 1 over the Hubble constant is the age of the universe. And we know that it explains the expansion of the universe. We can understand the expansion. And from knowing that, we can then calculate the distances. There's been so many different ways, thousands and thousands and thousands of ways in which we try to establish the constant to try and zero in on what that number actually is. And we still haven't achieved it. It's probably somewhere between 68 and 73 kilometers per second per megaparsec. But it is a constant during this time frame. Since we know that the universe expansion is increasing, we would expect that constant to change over time. But so we're talking about not even geological time, but astronomical time. In other words, 500 million years from now, the constant will be different. But in our lifetimes, in 10 lifetimes, in 100 lifetimes, that constant will be essentially the same during that entire period of time. So we can consider it a constant for the time frame that we're in. But if we could come back 500 million years from now, I would bet that constant will be somewhat different because the expansion rate, the expansion is accelerating. So it hasn't always been the same. And I think it's the same for the speed of light. I would think that as the universe is expanding and space is expanding, that the speed of light may not have been constant as well. And there's plenty of people that do believe that as well. And so we then need to take that into account when we start calculating distances to faraway galaxies, the age of the universe. All that needs to be taken into account and adjusted for, with the assumption that that constant may not always have been exactly the same. And so you're absolutely correct that it's a constant, yes, but then it's not really a constant over large periods of time. And we do have to adjust our calculations to account for that.
Okay, thank you very much, Prof. I have one question. I think that should probably be our last question, or that's that one. Someone says, here we are in the universe. We have scientists that are talking about parallel world, etc. Is there any bridge that can connect our world with other worlds? I think for brain, that could be this bridge. What do you think, Professor? So someone is asking if we could come up probably with any technology or a bridge of a sort that can connect our world with other worlds out there.
So that would definitely be fantastic if we could do that. To give you an idea, the fastest spaceship that we've ever built was the spaceship that was sent, that I think it's called the New Horizon, that was sent to take pictures of Pluto. And we got there in about 9.5 years from the Earth. Tremendous accomplishment. It essentially flew from here to the moon in less than a day when it took the Apollo rockets 3 days to get there. So we were able to boost up the speed of this spaceship and using gravitational assistance as it traveled past some of the planets to get there as quickly as possible. So 9.5 years to make it to Pluto, which is about, at this point in time, somewhere around 33, 35 astronomical units away from us. And then imagine that it's about 250,000 astronomical units away to the nearest star. So with our current technology, it would take us at least 50,000 years to get there. So obviously the interest is there to find a quicker way. Is there some, and people will say, well, what about a wormhole? What about a fracture in space we could travel through and be somewhere else and all that? And those are good things for science fiction movies, but can it be done in real life? And so we have not yet seen anything or come up with anything that make it seem possible that we could bridge these enormous distances in a shorter amount of time. Even if we could travel at 10% the speed of light, which would take so much energy, we know that's not even possible, but what if we could? It would still take 45 years to get there. So yes, you can see it seems impossible. And so therefore, the methodology that we're using to try and communicate with other potentially alien beings that are intelligent, that have been able to build these kind of technologies, radio telescopes is the best way to communicate. So sending a radio message that travels at the speed of light, and let's say that there's a planet 100 light years away where intelligent life has built radio telescopes, it would take 100 years for our message to get there, and then it would take 100 years for the message to come back. And so in a 200-year period, we could say, hi, how are you? And they say, oh, thank you, we're doing real well. How are you doing? And that conversation would take 200 years. So yeah, we have enormous challenges trying to reach out to potentially other civilizations if they exist.
Okay, thank you, Professor. I think we have about a few minutes to go, but let's take, if you could combine these two questions and then answer them for me, I'll really be glad. So the first one being that I think you spoke about twin paradox somewhere in your conversation. You have you have a twin that on the surface of the Earth, one travels in the spaceship at a speed that is significant as far as it's compared to the speed of light. And then both of them are going to say that time slow down in your frame, time slow down in the frame of the other. But definitely we know that special relativity is only true when you are in non-inertial frames of references. You're in inertial frames of references, non-accelerating frames. And so definitely the one that goes to space will have to slow down at a point in time and then 10. So acceleration is going on there. So observations that he make are probably incorrect. But my question is, do the biological processes that go on in our bodies, do they follow time? When we say time slows down, if the biological processes that go on in my body that I feel as growth, do they follow real time? Are they consistent with real time? So that if we're talking about time slowing down, does it mean I've also aged in reality? I've aged less in reality. Is that true?
Yeah, that is. So what you explained initially was the what they call the twin paradox. And so the argument was, because we see that in the laboratory, that if you travel in one direction, one person standing still and this person's traveling, when this observer who's traveling sees this person appears to be approaching them at a very high speed. And so that was the paradox. But the difference is, and you can again go to the GPS satellites, it is the object that is moving through space that's experiencing a change in time. The object that's not moving through space is not experiencing the change in time. So the person left on the Earth, if there's an atomic clock there, that atomic clock will continue at the pace that we're normally used to. You put the atomic clock on a spaceship moving really fast, that atomic clock will move much, much more slowly, as is everything else. It's not that your aging slows down. Your aging goes exactly at the same speed as it would if you're left on the Earth, except time moves differently in the spaceship. So all the biological processes, the atomic clock, everything else is simply following the time of the spaceship, which is much, much slower than the time left on Earth. So you yourself would not notice any change. You would live life, a year for you would still be a year, all that would be the same. But compared to a person left on the Earth, when you compare the times, that would be drastically different. So you could not experience it being in that new time frame. You just live according to that time, but the two times are very, very different from one another. And it's the person traveling through space at that speed that's experiencing the change in time. I think your image just froze, so I'm not sure if you're talking or not.
Maybe this.
There we go.
Thanks. So, and thanks to Sara Monk as well for her presentation on APS student membership. Thank you to all participants who made time to join this year's edition of Adventures in Physics. Hopefully, we'll come your way next year with the third edition. Have a wonderful day and then see you next year. Yes, we're going to stream that. We're going to have the video on YouTube, and so you could check it out on Prof's YouTube channel, or you could check it out on APS YouTube channel as well. Thank you. All right.
All right. Thank you all. Have a good day or good evening. All right. And thank you for inviting me.
You're welcome, Prof.